Hello and welcome to Exploring Background Radiation, K-12 Classroom Investigations, presented by the American Nuclear Society. This evening's event is part of our educator training program, specifically developed for elementary through high school teachers. I'm Mary Lou Dunzik-Gougar, Professor of Nuclear Engineering and Associate Dean of the College of Science and Engineering at Idaho State University. I also was a high school math and science teacher for 7 years before going to graduate school. And like one of our presenters, I'm a licensed senior reactor operator. I'm very pleased to be able to moderate this event this evening. Before I introduce our presenters, I'd like to cover a couple of quick notes regarding today's event. First, if you have any questions, please type them into the Q&A function rather than the chat. So use the Q&A function, and we will do our best to address as many questions as possible. The event will be recorded, and a link to the recording will be emailed to event registrants tomorrow. Certificates of attendance for this event are available on request. Please look at the chat for contact information. You'll send the requests to askanything@ans.org. For the educators in the audience, please let us know if you'd like an ANS member to visit your classroom, whether it be virtually or in person. Again, you can send your request to askanything@ans.org. And for ANS members, we have a new Nuclear Ambassadors program that offers members free training in K-12 nuclear education outreach. You can contact Uchenna Azibe at the email address, again, that will be provided in the chat if you're interested in training for your organization to become a nuclear ambassador. And finally, we ask that all participants adhere to the ANS Code of Ethics and Respectful Behavior Policy, which can be found at ans.org. And again, a link will be provided in the chat if you would like to review that policy. So with all those notes out of the way, I'm very pleased to introduce our guests. First, Ms. Candace Davison. Candace has been a STEM educator for more than 30 years, including at Penn State University, where she was most recently Assistant Director for Education and Outreach and Coordinator of the Gamma Irradiation Facility at the Penn State Radiation Science and Engineering Center. She was the first woman to be licensed as a senior reactor operator of the university's Triga Mark III reactor. Candace joined Penn State in the Energy Technology Projects Group in the Nuclear Engineering Department, where she developed programs and presentations on energy, nuclear technology, radon gas, and radioactive waste. She began developing teacher training programs a few years after arriving at Penn State, when she became the director of the Penn State Nuclear Concepts and Technological Issues Institute. It is actually as a student in this institute, as a teacher at the time when I first met Candace. She's conducted numerous courses and workshops for professionals, educators, and students of all ages through volunteer activity with many organizations, including the American Nuclear Society. Our other presenter is Zachary Van Horn. Zach is the outreach coordinator and senior reactor operator at the Penn State Brazil nuclear reactor. He spent many years working with Candace Davison and has given tours to thousands of students. With that, I will turn the event over to Candace and Zach, and I'll be monitoring questions as you submit them.
Great. Thank you so much. And I'm excited to be here. And this presentation is looking at background radiation. And that's something that we're going to explore today. We'll start with generally what is radiation. It's actually a very broad category, and it's defined by the transmission of energy via particles or waves. So again, that's a very, very broad category. It's lots of things transmit energy by particles or waves. Most of the time, though, when especially the American Nuclear Society people talk about radiation, they talk about something that makes this Geiger counter click, right? That's sometimes called nuclear radiation. Ionizing radiation is what we use. And that's what the Geiger counter detects, is ionizing radiation. And you can hear it's beeping a little bit. And that's what we're going to talk about today, background radiation. So where is that background radiation coming from? Well, radiation is everywhere. It comes from cosmic rays. And recently we've had a lot of activity, even enough to maybe challenge your cell phone or transmission. It comes from our bodies. And if anybody knows what's naturally occurring in our body that's radioactive, you may have heard of something called carbon-14 or radiocarbon, potassium-40. There's plants that have the carbon-14 in them and also bring up radioactive materials from the ground, the earth, the soil, the rocks, and radon gas. And then there's also other sources of radiation coming from medical exposure. So if you get an X-ray, you would be exposed to radiation and you would receive a dose from that. But one of the things is to make sure everybody understands that when you get your X-ray, you don't become radioactive. Okay? The radiation energy goes through you. There are certain procedures, medical procedures, that they might inject radioactive materials in you. And then, yes, you would be giving off radiation. There are some consumer products that also may have a small amount of radioactive material. The average American receives about 620 millirem a year due to all these sources of radiation. And again, you can see from the chart that rock, soil, and radon, that's almost 40% of our radiation that occurs naturally. The other thing I wanted to talk about was the electromagnetic spectrum. We talked about radiation being a very broad category: radio waves, light waves. Those are non-ionizing radiation. They won't make this Geiger counter click. But as you see on the spectrum at the very far end, where the waves get very short wavelength, and the higher frequency, that type of radiation, gamma rays and X-rays, can make this Geiger counter click because it will kick electrons off the atom, making ions. So at that end of the electromagnetic spectrum is the ionizing radiation that we hear with this Geiger counter. So we're listening to some background radiation here. And again, these are the sources that radiation, and it's not a constant. You hear some fast clicks and then some pauses in between, because even though in general there's a background radiation, there's a lot of variation depending on maybe whether this detector is in the right spot to detect the type of radiation. So the first thing to do in exploring background radiation is to get a sense of what's around you, what's in the laboratory if you're working in a lab, what's in the building where your students are, and find out where this radiation may be coming from. Well, we'll start with the first story, that radiation was detected on the hands of Los Alamos National Lab workers who did not work with radioactive material. And that was a pretty interesting thing, because where did this come from? And what they found was the investigation revealed they'd been playing racquetball. And there was actually a report on this investigation. It was in 1984. And they found some material on their hands when they did a forensic investigation of what is the radioactive material that was on their hands. And they found that it was actually, well, before we go there, does anybody have any ideas what might have been on their hands? And I think you can put it in the Q&A if anybody has any ideas. What might have been on the hands of these racquetball players? We'll see.
Nothing yet, Candace.
Nothing yet? Okay. Well,
Oh, here's one. Americium.
Americium. That's a good guess. That's
Sweat.
a good guess. Dust.
There are two guesses for radon.
Okay. Well, okay, the radon guesses are correct. It's actually the radon decay products. So when uranium decays, and this is the decay series uranium-238, there are many different steps along that decay path. But one of them is radium-226 and then radon-222. Well, all the material before radon 222 was solid, and now we have a gas, radon. The gas comes up into the atmosphere, comes up into above the earth because it can move. And then you see after radon, polonium, lead, bismuth, polonium, lead, bismuth, right? Going down to lead 206. So we've got just one instance of a gas that can move, and then the rest is solid. And what they found really were those decay products, the polonium, the bismuth, some lead 210, lead 214. So that's what they found on the hands of the Los Alamos workers. That was one instance. And what we find is radon is colorless, odorless, it's invisible, but it is radioactive, so it moves through things, and it can collect in enclosed spaces. So we're going to do an experiment figuring out how to collect the radon decay products. And in this image, we show the alpha decay from radon 222 going to polonium 218, then another alpha going down to lead 214, then two beta decays, bismuth 214, then up to polonium 214, then down to an alpha decay to lead 210, then bismuth 210, polonium 210, those are betas going up to that. And you can see that when we beta decay, we don't change the mass number, but we do change the element. And when we alpha decay, the mass number does change by 4. So we go from radon 222 down to lead 206, but we've got a lead 210 that has a 22-year half-life. Prior to that, most of those decay products have a fairly short half-life, mostly minutes, some seconds, microseconds. So these decay products is from radon 222 to lead 210 are decaying fairly quickly till they get to lead 210. And that's really what we're seeing is those decay products from radon to lead. So let's talk about how we might collect the radioactive particles from the air. There's a couple ways to do that. One is just taking an air filter from an air purifier, or we here at the facility, we have an air monitor and just taking that air filter and looking at that. Another one is bouncing racquetballs, just like they did at Los Alamos National Lab. Why does that work? Well, when racquetballs go through the air, they actually have an electromagnetic kind of, as you're pushing it through, you've got lots of speed, a little bit of electromagnetism, a little static electricity, and that will collect more of these decay products. And of course, the top one, which we're going to show you today, which is, I think, the easiest, maybe not as fun as the racquetball, but it's a vacuum cleaner with a coffee filter or medical gauze. So what do we need to do this? We need a timer, electricity, a vacuum cleaner, filter paper, and a radiation detector. So what we did was we actually did this ahead of time, but before we go into the video, I'll show our components. Just a simple vacuum cleaner, and I have one that has a nice little hose that we put the coffee filter on and just ran it for 10 minutes. So we'll show you the video of this experiment. And there I seem like I'm talking to myself, but I'm not.
I'm here too.
Our first attempt was with one coffee filter, but that was a little bit too, that didn't work quite as well. It wasn't strong enough. So we used two coffee filters and just a rubber band to tie it on to the vacuum cleaner. And then we ran the vacuum cleaner. And one of the things we did before we started was just to show that the filter was not radioactive. And because the vacuum cleaner is running, you can see that the hose is moving quite a bit. So we ran that for 10 minutes. And obviously the longer you run, and we're not going to obviously sit here for 10 minutes while this is running, but the longer you run this, the more particles you're going to collect. So we're fast forwarding through the video to get to the end. And here we are at 8.5 minutes, getting to close to 10 minutes. And then that's the end of where we stop the vacuum cleaner. And can you see me now? I'm not sure. Oh, that's where we stopped the vacuum cleaner. And then we tested the filter to see if it was radioactive. And it was much more radioactive than it started. And so our background count was about 18 to 20 some counts per minute. And then with the filter, it was a higher background count. So we'll show the filter and
Yeah.
so we ran the detector, ran this detector, and we took some counts, and then we reset and we counted, about 1 minute counts every 5 minutes, and then every 15 minutes. And as we're going down, we're noticing that the counts are decreasing over time. And this is one way to do it. We can also use the Geiger counter and show if it's radioactive using the Geiger counter. And the clicks are a little bit higher than background. And then if I put a filter to it, you can notice that they're higher than background. Okay. So what we did was we showed that the radiation detector, that the filter was not radioactive to start with. We did keep the filter in an envelope or plastic bag prior to starting, mainly to keep the radon decay products from, getting onto the filter to start with. So we were keeping it clean. We ran the filter paper, through the inlet hose of the vacuum. You could also, in the past, we've had people take air filters from, one of those air purifiers, letting it run for a long time. The main thing to keep in mind is what they call the average or the effective half-life of the decay products is about 45 minutes. So, if you're bringing something from home into the school, then you have to make sure that, you have less than 45 minutes before you start, because you're going to lose about every 45 minutes, you're going to lose half your radioactivity. Also, if you have a thin filter like we did, we found that we needed 2 filters to keep the, not tear. And we ran at least 5 minutes, but 10 minutes, 15, 20 minutes, the longer you run, the more you're going to collect. Then we turned the vacuum cleaner off and then looked at the dust on the filter and also looked at the radiation levels. And taking readings every 5 to 10 minutes, as I said, that's with a 45-minute half-life. And the other thing that we did, and we're going to show our Excel sheet that we used. And you might notice that some of the data, initially, we had some higher and lower numbers. But then as we went back over time, overall, the counts are going down, which is what we expect. And again, sometimes you might get a higher number than you did before because maybe there's some background radiation, extra cosmic rays that are hitting the detector, and then you have your error bars, if you put error bars on. But you can see Zach just put the last data point that we made on there. So it is trending downwards over time. And the physics teacher article on radioactive ball also shows this as they tried different rooms. So we'll go back to the what to look out for on this using this experiment. Radon levels vary over time, season, and also time of day. Certain times of the day, barometric pressure can affect radon decay levels, humidity can affect radon decay, radon levels, thus the decay levels, decay product levels. Typically, lower areas closer to the ground, sub-level areas would tend to get more radon collected gas. So if you can do the experiment at a ground level or subground level, you might have a better chance of collecting radon levels, radon decay products for your experiment. I know one school, the kids went to different classrooms, the gym, and they just, did their record. They hit the racquetballs around and did their recording. So again, it depends on the time of day, the humidity, a lot of different things, barometric pressure and things like that. So those are some experimental challenges. Even the one we did today, we didn't really see as much radon decay products as we expected. I know in the past when we've done this, the summertime, we tend to get a good number. Sometimes in the winter, because it's cooler and maybe the rooms are warmer, the gas will be moving around more, you'll get to see some of that. So even just seeing the differences over multiple days is one way to look at the radon decay products. This is, as I mentioned, we have an air monitor. This is from the filter paper. So how did they tell what material those racquetball players had on their hands? Well, they used gamma spectroscopy, and this is a gamma spectrum of that, of our air monitor filter paper. And you can see there's the bismuth 214 that we talked about, lead 214, and some other radioactive elements. So this is one way to verify that if you have a system like this where you can get the gamma spectrum, you can verify what you actually are collecting. And that is also one way at the Radiation Science and Engineering Center, if the background levels on our air monitor seem unusually high, we take the filter and we look at, well, what's on the filter paper? What are we collecting? And this is one way to do that. So the question I have is, true or false? The radon problem in homes generally, not due to uranium mill tailings or things like that, was discovered by accident when a nuclear power plant worker set off the radiation detector alarms at the plant. And does anyone want to put in the chat or the Q&A, put in the Q&A what they think? True or false? Do you have anybody?
Not yet. They have been putting other questions in. Let's give it
Okay,
a second.
that's okay. That's good. Are you ready for the answer? Sure. The answer is true. And this was.
Yeah, there's a combination of true and false answers.
Okay. And I was actually working at Penn State. This was in 1984. So that's, as they said, a long time. Stanley Watrous, if you look his name up, you will find out that in December of 1984, he set off the radiation monitors at the power plant, and they didn't have radioactive material. They were building the plant at the time, and there was no radioactive material on site. So they went to his home and found out that his home was higher than even a uranium mine is allowed to be as far as radon decay product and radon levels and decay product levels, which was really a surprise at that point. They didn't think that radon levels in general, just, without the uranium decay products and things, could get that high in a home naturally. So they used his home as a test case. How do we then mitigate radon from collecting in the home? And some of the things they did proved not to work, so they had to find a way to make sure it did work. Now, ironically, if Stanley had lived in either of the homes on either side of him, he would not have set off the radiation monitors, and we maybe still wouldn't know about how significant these levels can get in homes. So just a quick geology, the Limerick station is down near Philadelphia in southeastern Pennsylvania. And you can see there's some nice little light pink and some purple lines there. And that's called the Redding Prong. And it's a geological formation that tends to have a little bit higher background amount of uranium in it. The rocks there tend to have a little higher level of uranium. And so the homes around there tend to, because of this uranium decay, tend to have potentially have more radon. And you can see this map of Pennsylvania. The red is above the action level of 4 picocuries per liter. And if you remember the geology, that's about where that geology was. If you don't live in Pennsylvania, you can go to the EPA map of radon zones and see, where are the radon levels typically in your state, and find out, is my area potentially a higher area for radon due to, again, the geology and also testing that they've done over time. Well, what about the health risks for radon? The EPA and the World Health Organization have identified radon gas as the leading cause of lung cancer for non-smokers. And there's actually a synergistic effect for smokers. The Watrous house that I talked about, 2,700 picocuries per liter. The decay products were on his, his beard, his hair, his clothing. And one of the things I mentioned about that electrostatic, effect, polyester, which is not natural, it's a human made, it's got lots of plastics essentially in it, that will attract radon decay products better than, say, cotton. So if you wear polyester, you're going to be, that electrostatic could be attracting some radon decay products. So the Watrous house was way, way higher than the EPA recommendation of 4 picocuries per liter. And what is a picocurie? It's a number of emissions, right? And so you take a liter of gas, a liter of air, and you see how many counts you get. And so that's how they calculate. But there's different ways to actually figure out how much radon is in a home. If radon gas decayed directly into a non-radioactive element, so it went from radon-222 to stable lead, I can't do that, but just say it went to some stable element, would we be concerned about it as much as we are today? And why or why not? True or false? We would not be as concerned about radon if it decayed directly into a non-radioactive element, or would we be concerned? Just the same. And anybody have an answer in the chat, in the Q&A?
I'm seeing so far 2 false, 3 false, 1 true.
Okay. Okay. If it went directly from a gas to that stable solid, we would not be as concerned about it health-wise, because the radioactive gas, remember, it's a noble gas. It doesn't really interact much. It has a 3.8-day half-life. So the chance of you breathing in the gas and breathing it out in less than 3.8 days is pretty high. It's not going to, as a gas, it wouldn't tend to stay in your lungs, versus a solid particle would be more easily potentially stay in your, what they call the bronchial epithelium. So if it didn't decay into all these radioactive solids, we would not be as concerned about it. It's really those decay products, those solid radioactive elements the radon decays into, that's the health concern. And so therefore, the health risk of radon is really due to the solid radioactive decay products, true or false? I think I gave you the answer. So true. It's that those solid decay products that might attach to dust, get into your bronchial epithelium, and staying in and bombarding your lung tissue with alpha and beta particles. That's really the health risk of radon. But obviously you need the gas to get to those solids, right? What about National Radon Action Month and Radon Action Week? Did you know that January is National Radon Action Month, and October, the 3rd week in October, is Radon Action Week? And some schools do promote learning about radon, understanding the health effects and what it is. And there's a EPA has a resource page on this Radon Action Month and Radon Action Week. So there we are. We're to the point of questions. And we wanted to leave a lot of time because I heard that there were a lot of questions. So I open it up to where we want to start with that.
All right, here we go. First one. Where did you purchase the Geiger counter? This questioner would like to buy one, and they're also asking, are the ones on Amazon any good?
Ah, boy. Well, this one is actually, this has what they call a pancake probe. So it's a bigger area to test for things, but we do have smaller detectors. And there's a couple different, what do you want to call them? The suppliers, Pasco has their radiation monitor, also Vernier has radiation monitors that are typically used in conjunction with a lot of science lab equipment. Yes, you can get things on Amazon. There is a continuous radon monitor that you could purchase for your home to just see what your levels are, and you can see how ventilating can reduce the radon levels in your home. And that I think you can buy on Amazon. So yeah, Vernier and Pasco, which are the two typical science lab equipment, is what we've mostly used in our facility. And then the scaler that we used, that's Spectrum Techniques. Those are very old that we have, but they have much newer ones that you can purchase too. So that's, yeah.
And I'll add that be careful when you pick a detector. Some of them will only detect beta gamma. The ones that detect alpha, beta, gamma will be more expensive, because what Candace showed you there with that area through which the radiation would go has a very thin mylar window that has to be protected with a metal grid. When you have that mylar window, alpha can make it through and be detected, but that construction makes the detector more expensive. So just things to consider.
And I think we're talking like $200-ish, $150, $200 for the alpha, beta, gamma. You have to see, it'll say alpha, beta, gamma on it.
Right.
So.
Okay. If you use rocket balls, how long do you have to bounce them?
Again, the longer you bounce them around, the better your, hopefully your data will be. So they typically, I think in the radioactive ball, physics teacher one, I think it was 45, 50 minutes, because it was a class period. They just bounce them around for, science class, go out, bounce them around, come back, and then, take the reading. And then, then maybe the next groups did the data over time, depending on how long the lab is. But I'd say at least 30 to 45 minutes, and as your typical racquetball game. So, and the more they hit it, right, the more collecting you're going to get. So, exactly.
How about pickleballs?
Well, pickleballs weren't invented whenever they did. But yeah, I don't know. That would be, and again, outside your levels, atmospheric, and just generally are going to be lower than in an enclosed building. So,
okay. There's a statement here that maybe you'd want to comment on. I would assume that houses with known radon emissions give higher values, so low humidity areas will give higher levels of radon.
Say that again.
Yeah, so there are actually two kind of not connected sentences.
Okay.
First one is, I would assume that houses with known radon emissions give higher values.
Right.
Yeah, and then low humidity areas will have higher levels of radon?
It really depends on the geology, but if you have, what I was saying is, if like day 1 versus day 2, for example, in here, we did the experiment one day and we got a bunch of, good data results. And then the next day it was really humid and the dew point was high and all that. And our results weren't as good. And so it's not, humidity plays a role in where your baseline is, I guess I would like to say, versus, this area is going to have more radon because it's high humidity versus low humidity. It's really what you're coming up from the ground, which depends on the geology. And then, and also your barometric pressure, like the lower the barometric pressure is going to pull it up. When we had snow outside, so the gas didn't go out because the snow was keeping it, so the more gas came in. There's, or a wet ground, maybe it's easier for the gas to come into the building versus out of the building. So different things will affect how the gas moves into the building and stays there. And humidity just, puts a damper on a lot of things. So it's a general of, it's going to maybe reduce what you would have had if you didn't have a humid area.
Okay, that makes sense. But if radon is a gas, shouldn't its decays remain as a gas, or do they sediment somehow?
Yeah, that's the thing that blows my mind, right? You have this solid, radium-226, it gives off an alpha particle and becomes a gas. radon, 222. Now this gas particle moves around, and when it gives off its alpha particle, it's a solid. And you know, just like thinking about that just kind of blows my mind, because it's like, wait, it was a gas and now it's a, but you know, it's an atom. Atoms are very small. Now this little tiny, you know, solid atom can collect, you know, on dust particles or just slowly fall to the ground, you know, versus the gas that's going to move based on how gas moves. You know, think about PV, NRT.
Right. Yeah. And as you said, if the radon happens to be in your lungs when it decays, now it's a solid particle and it's more likely to deposit inside your lungs. Yeah. What about the evidence from Professor Leonard Cohen that areas with high radon level have lower rates of lung cancer?
Well, I know Bernie Cohen from the University of Pittsburgh actually looked at trying to assess based on epidemiological data of, he looked at women who did not smoke and tried to look at, you know, lung cancer. And again, it's a very difficult thing to do because you can't say this person, you know, got lung cancer from A, B, or C. But if they smoked, that could be a thing. If they didn't smoke, well, there could be other things. That's, you know, again, this is all basically scientists and epidemiologists saying, well, this area tends to have a higher background, especially the radon, the Redding prong, and we have lung cancers here. And so maybe, you know, radon was, you know, contributed to that, but they really can't say, you know, they got lung cancer from radon. But the data and statistics look to the potential that it is. And when they say the second leading cause of lung cancer, smoking is way up here and radon is like 10,000, 11,000, and smoking is over 100,000 deaths. So, you know, it's a big difference.
Yeah, huge difference.
And again, we don't have the exact data. That's
right. And it's a chronic problem because radon is low dose, like so many other things, you know, all the different sources of our background radiation. And there's just not data correlating low dose with results, with health results.
Right. Get into what they call the background noise. Oh.
Right. Question now, can the radioactive radon be removed from these homes safely? Do homeowners have to declare that they have high radon levels in their homes when they try to sell their homes?
Well, in Pennsylvania, it's actually part of the selling of a home. It's part of when you buy, and you have to test for radon or choose not, you know, to, if you're buying it, you could say, okay, I don't want to test, but most people do choose to test for radon. And the quickest way to reduce radon in a home is, they tried with Watra's house just to seal all the cracks, thinking, okay, we'll keep the gas from coming in. But there's tends to be negative pressure things like your bathroom exhaust fan, your kitchen exhaust fan, just the fact that the chimney effect from the home is several stories. So they found that just sealing alone does not work. So they put what they call a subslab depressurization system under the lowest level of the home, and they collect the gas before it gets into the home, obviously sealing above it so it doesn't get up there, and then removing it above the roof. And again, having testing afterwards to ensure that the radon decay products, you know, and the radon gas does not come into the home. One of the things that we have in our house is what's called a downdraft. If you ever heard of Jen Air back in the 80s, 90s, it was a big thing. Instead of having a, you know, vent above your stove, you just, you know, collect it and go down below. Well, that's a really strong fan, and it's going to pull a lot more gas, you know, from the earth into your home, because you have a negative, like a vacuum cleaner right on your home, right? So you're pulling that. So different things can affect how much radon comes into a home, even if you know, and again, the geology below. So there's lots of different things. But yes, you can test for radon, and some states require you to do that before you know, sell a home or buy a home.
Yeah, I think it is pretty much state specific.
Right.
There's a question about, how about rubbing a balloon on someone's hair and getting it static? And I guess the question is, will that attract enough of daughter products maybe that you could detect them?
Okay, yes. I would try it just see, again, the electrostatic and even the vacuum cleaner itself when it was running, because our vacuum is plastic, it can also be static magnet. And I would just say try. I don't, again, unless the levels are really, really high, I wouldn't expect it to, you to get very much in just a few seconds. But if maybe you got this electrostatic balloon and waved it around, and went around, maybe you could get some more decay products, but then you still have to have a way to collect them, kind of concentrate them into a smaller area or volume. But yeah, do an experiment.
Yeah,
right?
I think that's what I would say too. There's a comment from one of the participants that apparently he's tried the racquetball experiment, but claims it doesn't work very well in the East Coast humid environment.
Okay.
So that's feedback from somebody who's tried it. Doesn't the humidity entrain radon gas and result in higher levels?
Okay. I don't know the answer to that, but I do know up in the New England area where you've got a lot of granite rock, right? Well water, so the water runs through and then comes up, and then you spray the shower out, you're releasing that gas from the well water, right? So I know it can become entrained in like a well water, the subsurface water systems, because again, the gas is going to go to the place of lower pressure, right? It's going to be pushed out. There's different driving forces. It gets into the water and then it goes up. And if it's released in the home, then you're actually releasing some gas in homes. And they did find that in the New England area, again, because of the geology.
Okay, good. There are some NCRP documents listed, I guess, as reference for people relative to the health effects. So NCRP 93, 94, and 160, if you're interested in looking at that. Can you comment on the Radiacode 102 handheld gamma spectrometer?
I can't because I haven't used one, but does anybody else want to comment? I know a couple of our, we have a couple, things that we use locally, and they're as good as, sometimes they're pretty decent, but I don't know about that specific one.
Coffee filters in high radon houses, are there radon filters like air purifiers?
So what I was saying is you can use either a coffee filter, you could use the air purifier, that filter you could test, right? Because it's going to continuously bring those radioactive decay products onto just like a HEPA filter, right? Any type medical gauze some people have used. In fact, there was a group, a teacher that used the medical gauze, and they did the testing every single day, and they noted the temperature, humidity, barometric pressure to see again any correlation between those. So yes, anything that you can collect, products on, and certainly maybe even a piece of polyester, right? Because as you're bringing it through, that might even attract more.
Yeah, because it'll be electrostatic.
Right.
Does background radiation increase when we have solar flares, or does the atmosphere keep most cosmic radiation out?
We do see an increase, but we luckily, and the electromagnetic spectrum that I showed shows that a lot of the radiation from outer space we are protected from with not only our atmosphere, but our magnetic field from a lot of the cosmic particles, luckily. But yes, some do come through, and you can tell that whenever your cell phone kind of goes wacky with some of the solar flare events.
Right. Does radon, or more specifically, its decay products, collect on tobacco leaves? And does this contribute to the dangers associated with smoking?
There's some evidence that there are some materials taken up with tobacco leaves and also the decay products. But lately I'm not as familiar with what all that research has shown. But yes, I believe polonium is one of the things that when they looked at tobacco leaves, they've seen some of that, the decay products of radon.
That sounds familiar to me as well.
And it might be in one of the NCRP reports that I haven't read in a while, but yes.
Right. Yeah, look to NCRP. For those of you who don't know what that is, that's the National Council for Radiation Protection. And there's also ICRP, which is the international body. And NCRP and ICRP put out reports that discuss a lot of this. Comment, much of the East Coast, especially coastal southern areas, have naturally lower radon levels, which might have been why racquetball experiment didn't work as well. Okay, yeah, it goes back to combination of geology and all of the other factors. Could you suggest how to demonstrate this concept that you demonstrated today during a STEM night at a school?
Well, again, if you run the vacuum cleaner and then you can show the, if you have a Geiger counter and just show that it's radioactive, and you can talk a little bit about that. And, or if you have any kind of like the air purifier, you could talk about that maybe, because air purifiers aren't quite as noisy. And again, showing, background radiation and then showing the collection on the filter paper, or the air filter.
Yeah, I would recommend that. And you could have, again, because the vacuum cleaner is kind of loud, you might have one going in the background, but you can show, okay, listen to this coffee filter or whatever you have on its own, and then you listen to what it sounds like after you've used the vacuum cleaner. Same thing with a filter that hasn't been used yet and one that has been used, and just show the difference. I think that would be very effective.
And to say, in the early days of right after the Watrous House, when this became a big deal in Pennsylvania, people were scaring homeowners like to pay lots of money because they go in and they do this, right, and show, oh my gosh, we've collected radioactive particles on your. But again, that didn't quantify the level in the home. But some people that don't understand radiation, it would scare them enough to be, oh, whatever. How much do I have to pay to get rid of this? So yes. So
yeah, there were definitely a lot of scams about radiation radon remediation that really were they just were that. They were scams. It was unnecessary for people to spend the money they did.
And also they still say deadly radon gas, which it's not like carbon monoxide where you're going to drop over. It's a radioactive gas. And the deadly part, is potentially a long-term thing that we can't foresee. Oh,
right. And you can't, yeah. Okay. So the person who mentioned about filters was wondering, actually, rephrasing the question, could filters be used to lower the radon levels in a house?
The best way to lower the level is, for example, if you have a basement, you can just open the windows, ventilation, that's your dilution. The issue is the gas is going to collect, and again, your negative pressures are going to bring it in. So just using a filter, the gas is going to go through the filter, the decay products won't. So you still have the gas, and then you're going to get the decay products. So it's not going to significantly affect the radon. I wouldn't expect it to affect the radon level in a home, just filtering. You need to do the collection of the gas before it, gets into the home, or ventilate. I know a person that just opens the windows in their basement, whenever the radon levels get, above a certain point to keep the levels low in their home.
Yeah, that's what I've heard as well. Ventilation is really the most effective way. Modern homes are built to be so airtight, but then you exacerbate the collection of gas. So yeah, open your windows and let some air flow through. Comment, the elevated polonium-210 in tobacco is from the fertilizer used. I didn't know that.
Very good.
Home air filters are measured in MERVs. I don't know what MERVs are.
I don't know what MERVs are either.
Maybe some airflow. Okay.
But we have a filter on our little purifier, or even the furnace. You've got a little filter there, and I know people who have taken that and seen the decay products of radon on those. Again, you're just putting air through, so you're going to collect whatever solids are on that. And that's
Okay, here's a suggestion of using an old TV with a cathode ray tube. And after it runs for a while, the screen is electrostatically charged and it will attract the radon progeny. And then wipe that off with a
Wipe it off.
cloth. Yeah, that's a
That's a
great
good
idea.
idea.
Yeah,
Or
I agree.
any like even our LCD screen here gets an electrostatic charge. So, but certainly the old cathode ray tube, that's why you had to stand, 6 to 7 feet away from the very old televisions. But even new
Right.
TVs, that electrostatic charge is going to attract it. So that's one way is collecting. You could just wipe it down and collect it. Good idea.
Yeah, that is a good idea. Can radioactive radon be made to decay quickly into elements that do less damage?
We haven't found a way to change that yet. The decay, it's a 3.8 day half-life for the gas. And those solid, and one of the things I did not show on the decay from uranium, there's sometimes multiple, it branches a little bit. It doesn't always go a certain way, but it always ends up with that lead 206. So it might do an alpha and a beta or a beta and an alpha to get to an element, but these are solid decay products. And at this point in time, there's no way we know of to change the significantly change the half-life of any of these.
Yeah, the half-life
Maybe
is
someday.
yeah, maybe. Well, and I'll comment, I mean, unless you can somehow bombard a nucleus with
Right.
another particle, for which you would need a particle accelerator or a nuclear reactor, no, there really isn't a way to do that. And it's not terribly practical. Subslab depressurization is the best way to mitigate radon and decay products, right?
We have a slide of that on if you want to just show it real quick, we'll zip through and I'll show you that. Let's see if we get through. Can you get down to? It's right above the decay, I think there. That's the deadly radon gas. Here's the picture, the next one above, which I can't seem to, there we go. Mitigation strategies. So you seal any penetrations, cracks, whoops, go back to, can you put there? Okay, radon entry points, the previous one. Well water, chimney effect, negative pressure, that ventilation exhaust. And if you continue through the next one, I think is there. That subslab suction or depressurization, also venting the gas above the roof line. When they originally started after Watrous' house, they just did it at the ground level and they found the gas like that, and that was a concentrated gas, came back into the home, which is not good. So now they want you to vent above the roof line, again, then disperse it to the atmosphere. Yeah, good point. And this is part of the EPA Citizens Guide to Radon. There's a lot of documents from EPA that tell you what to do, how to test and mitigate.
So I'm wondering, for the teachers, will they be able to access these slides? Because obviously you didn't touch on every single bit of the slides.
Yes, I believe so. And Janice, what is she coming back? Is it time to come back on? Okay.
Hi. Yeah. Tomorrow, everyone who registered, including people who are not here enjoying this fabulous presentation, they will receive an email from ANS that shows that the recording is available. And along with the recording, we will post the slides.
Okay. Thank you. Good.
You're welcome.
Well, we have about 5 minutes left, and I'm not seeing any new questions. Uchenna, would you like to give an opportunity for participants to win a Geiger counter?
I'd love to. Big thanks to both of you all, firstly, for a wonderful webinar. And hi, everyone. I'm Uchenna, and I help facilitate ANS's K-12 programs and initiatives. And we're going to give you all a chance to win your own Geiger counter. These will be the CDV 700 models. So they're the old yellow, old school Geiger counters with the, detector. That's a metal thing that's attached. So here's how you can win. My colleague, who also helps me on ANS K-12 Programs Initiatives, Janice Lindegard. She's going to post some riddles. Oh, there we go. Thank you, Candace, modeling the Geiger
Yeah.
counter. She's going to post some riddles, jokes, depends on your perspective. She's going to post some, oh, there we go. See, and you too could be like Mary.
You too, yes.
Yes. So we're gonna post some riddles, jokes, etc., science-based in the chat. First person who can come up with the correct answer, we will reach out to you and coordinate getting you your own Geiger counter. So you'll see in the chat we've already got 2 posted. I think there are 4 total, so we'll go ahead and drop all those in. Just reply to the one you're trying to answer. Give us your best shot. And if you win, we'll ask you for your email, and through email, we'll get your address and get you a Geiger counter. So have at it. Best of luck.
Okay, good. And one thing I have to say though, this one is only beta and gamma. This does not, this detector does not do alpha because it has a very thick, it doesn't have that thin window that we were talking about that alpha would be able to get through. So it's beta and gamma only, but it still can give you good background readings.
Yeah. There's a comment that chat is disabled.
Yes, yeah, realize during webinar, sometimes participants can't answer in the chat. So go ahead and answer through the Q&A feature.
Good. All right.
Very light reading. Janice, you'll have to let us know what the right answer is. I don't have the answer. So I also could play if I didn't already have one, because you can put it down.
Oh, I like Roger says the chemist read the book on helium so fast because it was very light reading. I like that.
That's good.
I think that if that's the right answer or not, I think that deserves a Geiger counter.
I agree.
It's close to the right answer, but the right answer was put in by Emil.
Because they couldn't put it down. Oh yeah. Well,
have
But
two
light
winners for
reading. I mean,
I like
you
the
can
other
vote for
one
light
too.
reading. Okay,
Well-
Lillian is being ice is still H2. Yes, but that's not the joke, Lillian.
I'll hold up another Geiger counter that I have. This is also a beta gamma. Not sure what brand this one is. International Medcom. But this is just a beta gamma. And on the back here, you see the Geiger-Muller tube. That is the basic component of every Geiger counter. But it's a thick plastic window, so that's why it's only beta gamma. So
Yep, and then
go ahead.
oh, we have this one, which is a monitor 4 radiation alert, and there's a very thin, again, you see the protective, so people don't poke through, but yes.
Yeah,
This
that's
does
now
alpha,
beta
beta,
gamma. Right. So that would be more expensive than this one because of the alpha capability makes it more expensive to produce.
Okay.
H2 cold.
Getting some great answers here.
I know.
Yeah, let's
H2
see.
cold.
Emil got it right. I don't think anybody's gotten ice yet.
I think Roger had a pretty good answer though. I think we should reach out to him too.
Where's Roger? Where's
Right before
Roger?
Emil's answer.
Oh, they couldn't put it down. Yeah, yes, it was light reading. Yes.
I think that's good.
The ice is H2O cubed. Yes, there it is.
Oh,
Renee
someone
got
did.
it.
Someone did get that one.
And Emil got it.
That's
Did you guys
good.
look it up?
Renee says H2O cubed, so does Emil.
Yes. Daniel and Elizabeth and somebody else said there was no chemistry, and that's correct.
Now, William said for mitosis, the teacher was afraid the students would split.
That's kind of there. Yeah.
I like it.
I know, I like it too. The answer we were looking for was that it's a divisive issue, but
That's
But someone
that's a good
did
idea.
say that. I'm
What do you-
scrolling trying to find it. I saw divisive at some point.
yeah, me too. I typed in some answers to
Oh, okay.
some people, but
Proven, yeah.
yeah, so we will download the Q&A and everybody who won will win.
There we go.
Great. Thanks
And
for that.
it's 6:01.
Yes. So I think we will be cut off. Thanks to everybody who participated, and do feel free to email that address we provided. Oftentimes those questions get routed to people like me and Candace, and we want to answer everything we can.
Thank you.
Everybody have a good evening. Nice
Yep.
to see you, Candace.
Bye.
Thank you all. Bye-bye.